Okay, um, today we are going to be talking about dot products and their application in mainly physics. Now, I will warn you, um, I do a lot of like what I do in my channel could range from anything between factoring and I think that is like the complicated integral thing, like what was it called? Feynman's technique with sine x over x. I remember doing that, but this today we're doing dot products, and I'm not gonna go super complicated into it. Like this is mainly for 801 students or physics C students who have not taken Calc 3 yet. So 1803, right? They haven't taken 1803 or multivariable yet, and they have no clue what a dot product is, and they're approaching the energy and work unit, and then they suddenly have to do this weird operation that they have no clue about. So this is mainly to help people understand what a dot product is and how we usually apply that in physics and so on. So yeah, okay, let's start. Dot product. Let's say I have vector A, vector B. Oh, that's upside down. B. And let's say A is equal to components A1, A2. B is equal to components B1, B2. Now, dot product is an operation. It is like an operation like your multiplication, your additions, your logarithms, your differentiation. Differentiation is an operation, but it's on functions, not numbers. Like this dot product, we have like basically two operations that are unique to vectors: the dot product and the cross product. Cross product, if you're in 801, like I said, this is targeted to those types of kids. If you're in 801 or physics C1, the first one, classical mechanics, I'm not sure if cross product is really useful, because the only time I can really think of cross product being used in physics is Maxwell's equations, and they have to do with curl, electricity, magnetism, and that's a physics 2 thing, or mainly like an 802 thing, not an 801 thing. So that's a problem for another day. So for now, just this is I think dot product is a good thing to start, and by the time you take 802, I think you'll probably know what a cross product is, and even better yet, you'll probably know what curl is, and conservative forces, all that stuff. And so for now, lucky for you, we're going to do the simpler one, the dot product. And how we compute that is pretty simple. Say you have two vectors, A and B. To take the dot product, all you have to do is just multiply each component and multiply like each x component and y component and add them all together. So this dot product would be A1, B1 plus A2, B2. That's it. That's how you compute a dot product. Now, one thing I want you to notice is this strips a lot. This apparently, at least, is what I heard from my elders, teachers. This trips up a lot of students because they get they do an operation on two vectors and they get a number. But yes, you're gonna get a number, and you're wondering like what does this number mean? Because like if you're like doing this arbitrary operation and you don't know what the number, like what it actually tells you, we'll get to that. But for now, just know that this is how you do the operation. You just multiply each component and you add everything up. Remember, this is a scalar quantity, right? So if you want a dot product two vectors, you're finding this. You're just doing multiplying each component and you're adding everything up. Okay. But here's where dot product becomes kind of useful. The first thing I want you to realize with this is that it's really simple to compute, right? You're just multiplying and adding. Now with calculators, that's even easier, but this is like, if you know your components, this can be done like that. But the truth is, dot product is not only done like this. There's two ways you can compute dot product. So a second way you can compute dot product, which is actually, it's less useful for computing it, but it's more useful for the analysis and its applications. The way you would do it the second way is you would take the magnitude of A, which basically is, you would like A1 squared plus A2 squared, and you square root with that. So magnitude of A would actually just be the square root of A1 squared plus A2 squared. Basically, like if you're doing a Pythagorean thing, you're doing like, this is A1, A2, and you get another marker. A1, A2, right? You're kind of just doing Pythagorean theorem by just like finding the length of this. That's the magnitude. Magnitude is just finding the length of the vector. So yeah, trying to find the magnitude of A, or ignore this now. Find the magnitude of A, you multiply with the magnitude of B, and you multiply by the cosine of the angles of the angle that's in between them. So this angle is theta, that's in between them. You multiply by the cosine of that angle. So obviously, if I were to give you two vectors and I asked you which one, and I asked you to compute dot product, I think if you're sane, you're probably going to choose this method, which is right. You're supposed to choose this method, but this method holds usefulness because it gives the dot product meaning. Basically, this should remind you, physics students, of a lot of things, of breaking vectors into components. If I have, let's say, this vector A, and let's for simplicity say, let's have a unit vector this way, right? So the length is 1, and I have an angle, right, theta. I can use dot products to compute a cosine theta, which you're wondering, why would I want to do that? That's A in the direction of B. That's the component of A. This is A cosine theta. That's the component of A in the direction of U, right? Basically, just a simple multiplication and addition operation can give you an answer that you would normally have to use trigonometry to get. This is what the dot product means. The dot product essentially is how close together how similar the vectors are. The closer they are, the more similar they are. Therefore, higher the dot product, and the more larger they are and more similar they are, the higher the dot product. The more away from each other they are, the more negative the dot product. Basically, if I have, let's consider three scenarios. One where they're perpendicular to each other, the angle is perpendicular, BA. The regular scenario where it's like any angle, any random angle, A, B, and then an obtuse angle, so like this. A, B, B. Let's do the dot product now. If you were to do dot product for this, okay, let's start with this one. The dot product of this would be the length of A times the length of B, which we're not going to care about right now. But if you take the cosine of an acute angle, an angle less than 90 degrees, we're always going to get something more than 0, right? Basically, this is going to be greater than 0 for any acute angle. What that means is this is going to be positive, right? You can't really have a negative length of a vector, so this is always going to be positive. So what that means is, if the dot product is positive, the vectors are pointing in more or less the same direction, which means that basically they form an acute angle when they're together. This scenario where it's an obtuse angle, of course, again, positive, positive stays constant. Let's ignore that. But let's talk about the cosine of this angle. When it's more than 90, the cosine of the angle is going to be negative, which means the dot product is going to be negative. So this will make sense later on when we're talking about work. If the vector is in the opposite direction, its projection is taken away, right? It's taking away at the other vector. Like if I take this projection, it's kind of taken away, which is where the negative really comes from. And that's why the dot product really works for something like work. And for this one, obviously this doesn't matter, but this time cosine of 90 degrees is 0. So what that means is that if the dot product is 0, it means they're perpendicular, the vectors are perpendicular. Now again, if you took physics 1 and you know about work, then it should be obvious that obviously this should be 0 because it's perpendicular. But for those who haven't taken physics 1 and have no clue what I'm talking about, why this makes sense for this to be negative, this to be 0, and this to be positive, you'll see that right now. Here's where the dot product is useful. Formula for work, if you remember if you took physics 1 before, you probably know this, and you're probably realizing why I'm talking about the dot product being useful. Or if you haven't taken physics 1, this is new for you. But here, work as a definition, like F equals ma. This is work. Work is net force times the distance cosine of the angle. What that means is if I push a block, say I have a block, right, and I pull it with some force along a distance d, right? To find the work done by me, I'm going to take the angle, find the cosine. Basically what that is finding the projection along D, right? Take the projection along D, multiply it with D itself, and then, and that's your work. And the thing about work is it's a scalar quantity, it's not no vector. Scalar quantity looks a lot like the dot product. You kind of get where this is going. Work is essentially F dot D. Or in other words, it's the force vector dotted with the distance it travels. And if you're taking physics 1 before, the reason why we don't do the dot product thing is because A, it's a calculus thing, and B, you've been doing force constant. Basically, a guy pulling on it at a constant force at a constant angle. Life isn't that simple. A lot of real world, the force completely turns around, does a backflip, right? And we want to figure out the work done there when we can't really when the force is changing, right? And it's changing along a field. Here's where some hardcore Calc 3 stuff comes in, and I'll spare you the lecture. It's a little convoluted, but I'm sure a lot of people who are watching this can get it eventually. But I'll spare you the lecture. If force is changing, but obviously I'm going to give you like an intuitive way of where it came from. If force is changing, for example, force points this way, then 2 seconds later force is this way, and then 2 seconds later force is that way. Basically, what you can do is you're gonna you want to take the projection along the distance the block is traveling, and add everything up, right? I want to take the projection of force here, projection of force here, projection of force here, and add everything up. That's an integral. So another way to say it is if I take, let's change this D to R because I don't want to do DD or DR. DD, that just sounds weird. So let's just take little distances DR instead of DD. I want to add everything up. Integral work is essentially integral from position, or it can be any position, or the time where you're at that position, doesn't matter. but make sure this is a line integral. This is what we call that, of the force dot this. This is one of your fundamental formulas in physics.